Thank you for joining us for our latest installment of our 2025 webinar series. My name is Lori McLeod, President of NOVONIX Battery Technology Solutions, and I'll be your moderator for our webinar today. Today's webinar will be recorded and made available on our website. I'll drop in the chat now the links to our previously recorded webinars in case you're interested. And in just a few moments, we'll be hearing from two of our NOVONIX team members, Scott Duffett, Director of Sales, and Connor Aiken, Staff Scientist, as well as Jerome Babauta, Marketing Manager for Gamry Instruments. Today, the NOVONIX and Gamry team will be diving into how combining EIS with UHPC can unlock a deeper understanding of battery performance and degradation mechanisms. Our presenters will be walking through real-world data and case studies to showcase how this powerful combination is already supporting advanced battery research, validation, and streamlined workflows across the industry. Following the presentation, we will leave some time for questions. You can leave them directly in the Q&A feature at the bottom of your screen, and we will respond to as many as we can. Now, I'll hand it over to Jerome.
Thanks, Lori. Scott, next slide, please. So my role here is in about 10 minutes to talk to you about, EIS, why Gamry, and, what was the basis of this partnership, and maybe introduce impedance to you. So Gamry has been around for a bit, founded in 1989. We are headquartered just north of Philadelphia in a city called Warminster, Pennsylvania, in the US, and we are distributed across over 80 countries. I think the number is higher, and we basically operate globally. We have a new satellite office just based in Italy that helps support our operations in Europe. So Gamry, if you think about Gamry, we basically manufacture precision electrochemical instrumentation. And, on the right there, you see we make potentiostats, galvanostats, and ZRAs. And we're really known for our hardware and our implementation and everything about electrochemical impedance spectroscopy, so EIS. Next slide. So, historically, we were the first to basically make EIS accessible to the wider electrochemical field. In 1993, we pioneered this subharmonic sampling, and this is the reason why you don't need an expensive FRA. But basically, before Gamry, you could spend upwards of $50K, and after us, now you can get EIS for relatively cheap, right? The other thing that we pioneered was this idea of true ground isolation using optocouplers. And this was for another field, but it turns out to be extremely important for EIS integration. Next slide. So, we put potentiostats in computers. That was kind of the thing we did, and part of that was because of this floating and electrically isolated systems. And today on the right, we are now always advancing on the front of EIS at the limits, right? And that's both at the very, very ultra low impedance, right? Sub-micro-ohm differences, as well as EIS for huge battery packs, 1,000 volts, right? Next slide. So why EIS? Why are we having this integration? And that's because what EIS can do is measure snapshots of a battery's impedance behavior over its lifetime. And in doing so, you can gain insight into the battery's internal components, right, by tuning kind of the applied frequencies, getting things such as the ESR or HFR or a measure of the DCIR, and it's non-destructive, right? So you don't have to take apart the battery. And so a good example of that is on the right. Right here is your first look at impedance data. And this is a Nyquist plot, and it's for lithium iron phosphate battery and LFP as received. And so there are things about this plot that are extremely useful to track. And I'll introduce that to you in the next couple slides. So next slide. So impedance, right? It's basically this idea that you have this frequency-dependent resistance to current flow. And historically, or not historically, but you're more familiar with Ohm's law and how that works. But impedance is just more generalized form of that, okay? And when we talk about frequency, response of like resistor, capacitor, and inductor, what we're really saying is we're trying to figure out how these systems behave at different frequencies, but really at different times. And so that's the goal of impedance, and that's what impedance is. Next slide. And so what you want to do when making impedance measurements is you want to apply a small sine wave perturbation. It can be potential or current, and you have to do this at a fixed frequency. And then you calculate the impedance. You calculate it from the potential and the current. And you repeat this for a wide range of frequencies. Again, you sweep frequencies so that you can understand kind of the temporal response of the different battery components. And when you do that, you plot and analyze. Next slide. So this is what it ultimately looks like, the raw kind of input and output. In blue, you have an applied voltage, and in red, you have the responding or the resulting current. And right, if you have a linear system and you've done this right, when you inject a single frequency sine wave, you get a single frequency response back. Right? And this is a single period. Right? And that's why you have magnitude or the impedance on the y and time on the x. Okay. And so from these responses, you can calculate the impedance. Next slide. And so once you have done that experiment for multiple frequencies, you have to figure out how to plot it. And so there are two types, okay? And this is maybe what you see in the literature. You have a vector-based and a complex plane-based. And, it's basically two different ways to define a point in space, in two-dimensional space. And so the next slide, you'll see that, this is your typical Bode plot and Nyquist plot. And in this field, I think most people have interest in the Nyquist plot, so we won't talk too much about the Bode. But the idea is that you can plot the imaginary impedance on the y-axis and the real on the x-axis. And um, there's some utility in doing it this way. Next slide. So when we're talking about EIS and we've made the measurements, one of the things that you may be aware of is this idea that you can model the impedance data. And you can do that fairly easily, and it's accessible with, especially with the Gamry software. And what happens is you can model the battery parts, the internal components of the battery, or any other electrochemical cell as a network of these elements, a resistor, capacitor, inductor, a Warburg element, and then the bottom right is the constant phase element. Right? When you put them together, you get an equivalent circuit. And this is what you want to track over time, especially in integrations of EIS with cyclers. And next slide. And so the basis for this, right, is this idea that you have, Scott, you have to kind of click through this. Well, so the basis is that every electrochemical interface has three components: a double layer capacitance, an electron transfer resistance, and this RU uncompensated resistance, right? They form what's called a Randall cell. And this Randall cell is the simplest way to describe an electrochemical interface. Next slide. And so you can envision that there can be much more complicated models, especially since there are so many elements to batteries and other electrochemical devices. And so this is definitely out of the scope of the time that I have. But one of the three guiding principles you can think of today is that, when you build an equivalent circuit, it should correspond to some specific activity or a component of the battery itself. You can't just add elements to make the fit better because that's always true. And in fact, it's the opposite. You should use the simplest model that fits the data. So the next slide, right? Here's kind of an idea of how the Nyquist plot works, right? From the right to the left, we have this low frequency going to the high frequency, and where the impedance response trends towards the real axis or the x-axis, right? You see RU, the uncompensated resistance. You can resolve that there. And then this RU plus RP gives you basically the total resistance of the system. And so this is how you can pull out elements like the ESR and the internal resistance of the battery. In the next slide, right, You can see how this looks for now this LFP battery that I shared with you earlier. On the left is the Bode plot, on the right is the Nyquist plot that I shared. And so you can get this battery as received, run impedance on it, right? And from the spec sheet, you can see that the nominal resistance was about 180 microohms. That was measured under certain conditions. But if you orient yourself on the right in the Nyquist plot, where the data points cross the zero on the y-axis, that's your HFR, and that's about 200 microohms. So just from there, running a single impedance test, right, you can pull that out right away, and you can track that over the battery cycle life, for example. On the left is that Bode plot, and you can see that the inset is this equivalent circuit. And this is the equivalent circuit with the least amount of elements that can fit this battery's impedance response. Why does it look the way it does? And maybe we can talk about that after in the Q&A section, or maybe we can have a following discussion. But this is done with the software. You don't have to, right? So this already comes with the potentiostat, and this ability is pretty easy to do, right? Next slide. So while EIS is very powerful and you can do things like fit the data and pull out these elements that reflect the battery's internal components, right? There are some important criteria you have to consider. One, the system has to be linear, and this is going back to the response, the signal and the response, right? If you inject a single frequency sine wave, you expect a single frequency response back. If you don't, you have harmonics, and that's bad, right? So you have to know when to look out for that. Stability is also a key, and I think the integration is key here, right? You get stable behavior when you have a very good integration, and I think that's what we have here in the system that we're sharing with you today. And lastly, causal just means that the response that you get back is caused solely by the response that you, or the system, the signal you inject. Next slide. So, so it's important to also recognize, right, that not all potentiostats can run EIS equally. So one of the things that you always have to be aware of when you think about an instrument like a potentiostat or galvanostat that's EIS capable is this idea that there's an accuracy contour plot and a limit to how accurate it can measure an impedance value. And so on the right is an accuracy contour plot for the interface 5000. This is one of the potentiostats available with the integration. And you can see in the low impedance region, right, this system that's only it's relatively kind of cost effective. It can measure sub-milliohm impedances very easily, right? But you have to be aware that when you make an impedance measurement, it has to be within the range of this accuracy contour plot. And so, and I think that's it from me. So.
Thanks, Jerome. Hi, everyone. I'm going to introduce NOVONIX UHPC for those who aren't familiar with us and share some information about our products before Connor jumps in to talk about the integration. So if you've heard about the NOVONIX group, we do have a couple different entities, but how I generally bucket us is we are both a materials as well as a technology, battery technology organization. So we have an anode material division in Chattanooga, Tennessee. We have a cathode material division here in Halifax, Nova Scotia. And then our whole battery technology solutions division is also here in Halifax. Within the BTS division, where we'll be speaking most about today, is our cell prototyping and testing services, which is a full R&D outsourcing option for customers that need help with that. But what we're really here to talk about today is our ultra-high precision coulometry testing equipment. So let's talk about UHPC. So ultimately, UHPC offers the highest current and voltage accuracy and precision equipment on the market. There's a lot that goes into that sentence, and we're not going to be able to cover it all in the next 10 minutes as I introduce this. But what I do want to highlight is that we've been producing a lot of content in the past 6 to 8 months that is available on our YouTube channel. We've done different activities with the Volta Foundation, webinars with Voltaic, our own presentations from IBSE and other conferences. So all of that's available on our website and all of our main channels. So I encourage anyone that wants to dig deeper into this content and why we can make the claims about our accuracy and precision to check out this content and reach out if you want to have a further discussion. Ultimately, how we do what we do is we just have the most accurate source and sense for both current and voltage. And this has been a big focus of our development. And when you want to do very accurate measurements on your cells, you need to know that you're delivering the exact amount of current that you're telling the cycler to deliver. So this is something that we focus a lot on. Every cycler has its place in the market, and for us, we focus on this ultra high precision as a way to save time and to do things much quicker in terms of iterating on your development. So how this plays out in a short period of time is when you're looking at any cell testing data in the first 20 cycles, depending on the cycler you have, the data, the spread of that data can be quite varied. And when testing commercially available cylindrical cells that are from a tier one supplier, you would expect the Coulombic efficiency data to all be exact, even in the first 20 cycles. But other cyclers don't have the ability to really narrow in on these results and give that clean data. But when you look at this results, this black line in the middle here, that's the NOVONIX UHPC measurement. And this is what Coulombic efficiency should look like on multiple different cells from a tier one supplier in even just 20 cycles. So this is how we do what we do, and how that really plays in the real world is it just enables rapid decision making. So everyone is familiar with doing cycle life testing and looking at cells as the capacity changes over a 3 month, 6 month, 12-month cycle, and seeing the different groupings of cells separate over time to kind of show your winners and your losers, so to speak. But we enable customers to do this screening much more rapidly by leveraging our highly accurate and precise systems. So this was an example of an electrolyte study where the green and the red cell had some additional solvents in it that provided a much more stable, electrochemical balance, which then performed in a better lifetime in both the long-term cycling, but in the first 25 cycles, you can see Coulombic efficiency was much higher on these cells, and it played out. So we have many, many examples of this. And again, I encourage you to check out our other content where we share countless examples of how this plays out every day in the industry. And when we talk about UHPC, Coulombic efficiency is a very common metric that we bring up and talk a lot about, but Coulombic efficiency is not the only thing. It's really made up of a couple components, and that would be charge endpoint capacity slippage and capacity fade. So while most people are likely familiar with capacity fade, slippage is a relatively new and I would say upcoming precision metric that people are focused on right now. And if your equipment is accurate enough, you're able to actually measure slippage. And what we're doing is we're counting these extra electrons that are being sent through the external circuit during the charge. And these are generally indications of some of these invisible failure mechanisms that could be happening through that process. If you ever seen a cell chugging along just fine and then rolls over or has that knee point, but there was no indication in the fade early on that there was issues with this cell, that is an indication that there was higher slippage. But most cyclers on the market today aren't able to identify this and really report on it accurately. But the NOVONIX UHPC is certainly able to do that. So when we think about Coulombic efficiency or Coulombic inefficiency, we like to think that this is really an equation built up of in terms of how much slippage is happening as well as fade. And by using these metrics, you're going to be able to really lean into some lifetime prediction and other issues much faster than you can on a traditional testing equipment, which will certainly accelerate any R&D that you're doing. So just to say, obviously a lot of that's showing the plots, but this equipment in itself, We generally ship everything turnkey, rack mounted, so there's no assembly acquired by our customers. We have three different channel modules or cyclers. We have one for 2 amps, up to 10 amps, and up to 20 amps. So depending on the type of cell you're working on or the different goals you have for your testing, we'll make recommendations based on that. But all three of these are great options. Really just depends on your goals in testing. And then we also make all of the thermal chambers, cell fixtures, everything else. So it truly is a single turnkey solution that allows our customers to have a fully integrated system. And in terms of that integration, we'll be talking further in the next few slides of how we've now added the Gamry capabilities to this overall solution for an even better integrated solution. So with that, I'm going to hand it over to Connor to jump in and take this further.
Thanks, Scott. All right, if we could advance. Yeah, so I think this is the first slide where we actually get to kind of show off this integrated system that we're really proud of and kind of start diving into really how simple it is, but how it works. So what we're providing in tandem with Gamry is a fully integrated solution. So we're calling out here that it's both a hardware solution and a software solution. I'll kind of run you through the graphic on the right, kind of from the bottom up, I guess, because that makes sense, is there's one of the rack-mounted Gamry EIS box. This is a 5000 in this case. There's 8 channels on this. It pairs up really nicely with what's next in this stack if we move up, which is a NOVONIX 10 amp UHPC. These are kind of tied together. The only kind of new piece of hardware that's introduced that enables this integration is the fact that there's a cable that can connect one UHPC channel and one Gamry channel into a single position in one of our temperature boxes, which is the next item if you move up in this stack. So the system here will be set up for 8 channels as it is, 2 cables feeding in per channel. And like Scott said, everything comes rack mounted and it's really kind of a very tidy unit with a pretty low footprint. So all of the Gamry functionality, or nearly all of the Gamry functionality, is available in NOVONIX's UHPC software. So things like galvanostatic EIS, potentiostatic EIS, the experiments that Jerome laid out in his in the first third of this can all be executed via our software. This is really, really nice because in our software, we can also interface with our IP connected temperature chambers. So then you can do very complicated and involved experiments that really give incredible data with things like controlling the cycling temperature, having that be separate from the EIS temperature. And the key thing here is that everything is automated. So once a test is kicked off, there's no human intervention. So I think both Scott and Jerome have mentioned this, but it's good to repeat here that the device compatibility on the NOVONIX side and the Gamry side is really quite high. You can have any of the NOVONIX cyclers, our 2 amp, our 10 amp, our 20 amp, along with our thermal chambers. And you can pair that with all of the Gamry devices listed here. And the great thing is that a lot of people have this hardware, both from NOVONIX and Gamry, already in their lab. So getting this kind of integrated solution up and running would simply be getting a new cable from us and really just enabling a few options that already are probably in their software if it's already up to date. Next slide, please. Yeah, so this slide just demos what I introduced previously, how the Gamry potentiostat can be controlled from within NOVONIX's software. So the left panel here shows an image of our protocol designer. And in this case, step 2 shows both an EIS step. So in this case, what's highlighted is the fact that a galvanostatic EIS test is going to be executed. And when the user clicks this configure button, there's a small window that pops up that allows the user to input all of the relevant EIS parameters. And for anyone that already has a Gamry device, you'll notice that all the inputs here are the same as what you can input in the Gamry software. So it's very, very similar, and any user that's familiar with that would immediately be able to kind of get up and running with programming experiments in our software. So that's on the protocol side of things. To kick off one of these tests in the NOVONIX UHPC control, the only other thing that has to happen, which was the software tweak I mentioned, is that the channels that are connected to the Gamry devices have to just be kind of linked up manually. So there's the ability to right-click on a channel and assign an EIS device. The Gamry hardware is kind of automatically scanned for and found, and you just have to kind of, if it's a multi-channel device, for instance, like an EIS box, you have to designate which EIS box channel is connected to which UHPC channel. But other than that, it's incredibly simple. So I think Scott and Jerome both kind of did a really good job of explaining why UHPC and EIS respectively are such powerful techniques and why they're so useful to battery scientists. But I think the really awesome thing is that we can now start talking about why the marriage of UHPC and EIS is really providing a combined and integrated system that can do more, how complementary these techniques are, and how they kind of provide a complete information set that couldn't really be provided with any one technique alone. So on the right-hand side here, we've tried to put together a bit of an alignment chart to put in some of the typical quantities that you might see in a battery test lab, and place them on a pair of axes here, depending on if they tell you things about the reactivity or the stability of the cell, or maybe the kinetic performance of the cell. So that's the x-axis here. And the y-axis tries to place some of the techniques in terms of, are they for more fundamental research, R&D, quick diagnostics, or do they kind of get into the realm of quality assurance, quality control process, or even further up on this y-axis into things like field testing, validation with an application in mind, that sort of thing. And then on top of all of this, we've layered a color scheme on that tries to indicate, if you refer to the color bar on the right, just how fast the information can come in. So like Scott was saying, one of the key advantages that we really promote with UHPC is that it lets you make decisions really quickly. That's captured here with the fact that it's green, for instance. We've also labeled EIS green here. Typically, in our lab at least, an EIS experiment can take less than 10 minutes per cell, and it provides kind of a full information set, and you don't need to go for any longer than that. So you can kind of see how they're down here at the bottom, rapid decision making, they're green. Other things like Scott mentioned, long-term testing is kind of, we've highlighted here that it's a bit slower. And the other kind of calendar aging, rate testing, pulse testing, they get a little bit faster the whole way through. But really what we want to highlight is the fact that UHPC and EIS, they both give you information rapidly, but they're at opposite ends of this kind of spectrum of probing stability and reactivity versus kinetics. So the combination of the two lets you kind of provide a very full characterization of your cell. It will be quick. And really two of the things that I don't know if have been mentioned much, but as a battery scientist, things that I value are things like UHPC is very electrode sensitive. Scott hinted that we tend to break measurements of Coulombic efficiency down into their two root causes, capacity fade and charge endpoint capacity slippage. Typically, when we're making decisions and designing improved cells, we tend to associate things like capacity fade with problems with the anode. Charge slippage is problems with the cathode. So with a technique like UHPC, you can start to figure out, is your cathode good? Is your anode good? To complement this really well, Jerome mentioned that EIS is sensitive to kind of all the internal components of the cell. So every phase and every interface, if you make the measurement properly, has a signature that EIS can pick up. So the ability to kind of zoom in and see what's going on inside the cell with the combination of UHPC and EIS is really unparalleled. So it's really kind of a perfect combination. Next slide. So yeah, on top of all these basic kind of, maybe not basic, but reasons why these two techniques make sense, I think there's a couple of extra use cases that really demonstrate things like increased convenience, or just demonstrate really the power of what you get when you combine a high quality cycler with an EIS capable potentiostat. So we'll go through that on the next, I think, 4 slides or so. The first one's shown here. And one of the things I think is most valuable is when you combine these, you can start to perform EIS as a function of the cell state. So I think the most basic example of this that people will almost immediately think of is you can do EIS as a function of state of charge. That's what is going to be demoed on this slide and the next, but you can also do a lot more. You can start to perform EIS in terms of state of health. So as your cell ages, as it becomes older, you may want to routinely perform EIS and get a sense of how the features that are measured in the Nyquist spectrum, kind of how they evolve as a function of time or cycle number. You can do things like altering external conditions on the cell, how much pressure is applied to a pouch cell, for instance. what the environment temperature is, that sort of thing, and noticing how the EIS changes. So because you have this full integration between Gamry's potentiostat and our UHPC system and software, you can kind of interleave these EIS measurements into a battery testing protocol that you otherwise would have been already executing. So an example of this is shown on the right. This first graph here shows a voltage profile versus time of one such experiment. The protocol is kind of laid out here in words for reference, but what's happening is simply the cell is being cycled a little bit, and then we're zooming in on one cycle where you can notice a little bit of different behavior. The cell is charged from 2.8 volts up to 4.2 volts. And then on the discharge, which starts at about hour number 70, you can see that the voltage profile starts to get a little bit wiggly. What's happening here is that every 5% SOC, the cell is being interrupted in terms of the discharge to run an EIS measurement. So this is kind of the functionality that is enabled by this combined system, is that you can use the NOVONIX system to do this very precise high resolution charging, but you can tell it to stop, and you can switch control over to the EIS unit, make that measurement, and then resume your discharge or your charge. Next slide, please. Yeah, so this is the results of this experiment. This very brief kind of proof of concept are shown on the right here. So Jerome has already kind of walked us through the very basic understanding of what a Nyquist plot is. And I think for the purpose of this this session, what we can just show simply is that kind of the shapes are changing as a function of state of charge. So there's a color scale here. The 0 to 50% SOC ranges in the bottom panel, the 50 to 100 SOC ranges in the top panel. And the key takeaway is that notice in some of the paler colors, the spectrum is either bigger, some of these features are more to the right, and the same is, so this is kind of happening at 5, 10, 15% below SOCs in the bottom panel, or 85, 90, 95% in the top panel. So you can map out the impedance as a function of state of charge, and this will guide you in terms of things like deciding how to use your cell in a real device. So a couple suggestions that are put down here are that if you know the impedance is high at high SOC or low SOC, you could maybe design a fast charge protocol to suit such a cell. And this is what's done in devices already. So I think a lot of people that have electric vehicles, for instance, know that you can fast charge from maybe between 20% and 80% SOC, but not from 0 to 20 and not from 80 to 100. It's because the impedance gets large at these SOC ranges. Alternately, if you were iterating through a development cycle, you could maybe take this knowledge and try and find ways to improve on it. So you could, how can we improve the impedance above 80% SOC, that sort of thing. And you can also perform this impedance mapping as a function of SOC as a function of other variables. So as cells age, as your device gets older, can you still support fast charge like you did when it was first sold? That sort of, getting at that sort of question. Next slide, please. Yeah, so another really awesome feature of this combination, and something that I value personally quite a bit because I'm working in the lab with these systems, is how the increased automation of this integrated solution really translates to reduced time and labor. So on the right-hand side of this slide, we've kind of laid out a flow chart for essentially the same workflow that is completed on two different test systems. So on the left, there's a workflow for the integrated NOVONIX and Gamry cycler and EIS system, and then there's the one on the right for a discrete, separate, non-integrated cycler and EIS system. In this flowchart, anything that is green is something that can be executed by the system or by the computer controlling the system, whereas blue is something that requires human intervention. So the test protocol here is just kind of simply having some cycling and then measuring EIS before or after. Or before and after, excuse me. This is a very common use case. The EIS is there to kind of probe into the cell. The cycling can provide UHPC metrics, but another function of the cycling is to age the cell. So the purpose would be measure EIS before and after and see how those spectral features evolve as the cell matures. In the left case, all that's really required from a human is to put the cells in the temperature box and kick off the tests in UHPC control, assuming that kind of a protocol has already been developed with the relevant EIS parameters. From that point onward, it just runs seamlessly, and a human is only required to intervene once the tests are over to kind of clear out the old experiment. In the right-hand case, with separate pieces of equipment, it's necessary for a human to, of course, load the cells onto the EIS system, but then when those experiments are done, there has to be a transfer to the cycler and then back to the EIS system afterwards. This doesn't seem all that arduous, but it seems like more often than not, these steps where humans are required to intervene, you can't always control when the cycling finishes, when the EIS finishes, that kind of thing. If a human is required to transfer cells at 8 p.m. on a Saturday, the likelihood that there's someone working at that time, it just doesn't tend to line up. And you might lose 2 or 3 days to that alone. So the fact that you can set up a fully involved test with multiple different techniques means that increased automation, reduced human involvement, which means your test can kind of be finished when it wants to finish. On top of all this, we kind of want to mention too that if you have cells on our system with this integration with Gamry that are doing different protocols, assuming they're not lined up at the start, maybe you have 2 cells that start on a Monday, 2 cells that start on a Wednesday, we do have a queuing system to manage the handoff of control between our system and Gamry's hardware. So it all works very well, and it doesn't kind of break up the seamlessness, and it means the automation is fully robust and highly convenient. Next slide. Yeah, so one thing that I think is incredibly useful, and hopefully our customers find it useful too, is the fact that this integration is highly synergistic with our software-controlled thermal chambers. So our thermal chambers are sold with a temperature controller that is IP connectable, and therefore you can set the test temperature as a step in a NOVONIX cycling protocol. The reason this is important is because temperature is a parameter that can make both cell cycling and EIS measurements more effective and can speed up the amount of time it takes to get relevant information. So the remarks that I've kind of called out here in the second bullet point are that cell degradation, kind of the electrochemical instability of the cell, is increased at higher temperature. So oftentimes you'll see literature where people are doing UHPC experiments or even just long-term cycling experiments at temperatures beyond room temperature, so something like 40, 55, or higher. And the reason that's done is because electrochemical reactions tend to pick up at a higher temperature. They often follow an Arrhenius temperature dependence. So it allows degradation to happen quickly, and it means that you can establish differences between 2 different cell types very, very quickly. Might take a lot longer at room temperature, for instance. Kind of unfortunately, but it's just the way it works, is to tell differences in impedance spectra, you actually need the opposite temperature. So because impedance tends to probe things towards the kinetic end of the spectrum, kinetics are sluggish at low temperature, or at least ion kinetics are. And that means that performing EIS at low temperature can actually kind of increase the difference and help differentiate different cells. So with that in mind, you'd ideally, for maximum throughput, fastest decision-making, fastest rate of information generation, you'd like to cycle your cells at high temperature and then cool them down to low temperature so you can see the biggest differences. And just to illustrate this point, what's being shown on the right-hand side of this slide here is a series of Nyquist plots measured from the same cell, and the difference between each plot is the temperature. So the panel in the top left has 15 degrees, moving to the right and down to the bottom, all the way up to 45 degrees. And what you can see is there are features, specifically a semicircular shape that is conventionally associated with some sort of charge transfer, which gets bigger as the temperature decreases, or oppositely, almost disappears when you're measuring at 45 degrees. So if you want to get the maximum information and probe as many of these interfaces that Jerome mentioned, you can kind of measure inside the cell, it's just way more valuable to be making your EIS measurements at lower temperature. Next slide. Yeah, so I think it's really neat that we kind of have laid out a few of the kind of benefits, improvements to quality of life, and just why this combined system is so valuable and what it can do. It's something to me that I think I'm very proud of the fact that we have a customer story that we can share, and it seems like they're putting nearly all these ideas into practice. So what I'll go through in the next couple slides is a customer story from Dalhousie University. I believe they were our first customer for this integrated system. This was delivered to them just before Christmas of this past year. And before we even dive into it, we should acknowledge and thank Jeff Dawn and JJ Abraham for the data, the graphs. They kind of made everything and provided it to us, and they were more than willing to have us talk about how happy they are with their system. So in terms of what they have in their lab, it's kind of featured here, but the picture maybe doesn't do it fully justice, so I'll quickly go through it. They have two Gamry interface potentiostats. They're kind of standing at the top of the stack here above the computer monitor. The interface modules are single channel units, but can be extended out to 8 channels by using Gamry's IMX8 multiplexer. So there's 2 of those. These are paired with 2 NOVONIX 2 amp UHPC modules. And then there are a couple of NOVONIX 16 position temperature chambers, and these have the software controlled temperature controller in them. So it's essentially a 16 channel system, and there's a little bit of surplus temperature chamber space so that they can operate at 2 temperatures. Next slide, please. So in terms of what Dalhousie was looking to do with this, they laid out their motivation. They're doing some studies on electrolytes in high voltage cells. They're calling out high voltage here as specifically charging to 4.45, which I think it is indeed quite high. And they're studying the role of an electrolyte additive. So their test protocol was to perform EIS at 10 degrees. 10 degrees is low temperature, again, to kind of exacerbate the differences between cells and kind of make the EIS measurement more efficient. And then they're doing a C/20 cycle to check the capacity. Then a larger number, 20 C/3 cycles at a higher temperature to kind of age the cell. And then they're repeating. So the idea is that every 20 or so cycles, there's an EIS measurement performed, and they will kind of look at how that spectrum evolves as a function of cycle number and a function of time, and use that to gauge the performance of this particular electrolyte additive under high voltage exposure. Next slide. So the left panel here and the right panel show the right graph show the exact same information. One is just a zoom of the other. So to kind of walk through what was detailed on the previous slide, you can see there's a single slow cycle is what's in the top left panel, followed by a bunch of kind of rapid up down stuff. So the details of the voltage profile during the C/3 cycling kind of get lost due to how fast they are relative to the entire protocol and the width of the x-axis. While this is happening, you can kind of look at the bottom graph there of temperature versus time. So you can see during the cycling, the cell is at 40 degrees. Again, this is to exacerbate the aging and kind of stress the system electrochemically. Then the cell kind of charges up to 50% SOC. I think they were using 3.8 in this case. And the temperature for one brief moment cools, or it looks like a brief moment cools down to 10 degrees. This is highlighted on the right here with a little bit more detail. So you can see effectively when the cell reaches 3.8, there's some delay. All that's happening here is some queuing. There's a bunch of cells in this test. They all have to reach 3.8. And then the temperature cools down to 10 degrees. That's when the impedance is measured. You can actually even see the impedance in the voltage profile is a very small kind of jitter where the voltage profile gets a bit wider. But then the cells are heated back to 40 and cycling resumes. The next slide. So here's the results that JJ and Jeff provided to us. So there's kind of this is an example of the combined data that comes out of a system like this. You have one set of cycling data and another set of EIS data. The EIS or the cycling data is on the left. The key takeaway is that in the top 2 panels, for instance, there's capacity shown, and in both cases, the red data series, which represents the cell containing this additive, is higher. The control cell, which has no additive, is lower. So the additive is kind of making sure the capacity retention is a little bit higher. It suggests the system is a little bit more stable when the additive is used. And then if this is compared to the impedance data on the right, you can see that the spectra is changing for the top panel with the black data series or the grayscale data series. This is the cell without the electrolyte additive, so the impedance is changing. This suggests some of the interfaces inside the cell are a little bit unstable. The data in the bottom right panel, which is for the cell that contains the additive, the Nyquist spectra is really remaining mostly unchanged as cycling goes on. And I think the intention is to have this experiment go on for much longer than 40 cycles. This is really just preliminary data. So I imagine these changes, this difference in capacity retention, that's different in EIS spectra, stability, it's going to become a lot more obvious as well as this experiment goes on. Next slide. Yeah, so I think to kind of close this off right before we dive into the Q&A, we can just kind of provide some really high-level summaries. We're really proud of this integrated UHPC and EIS system on the NOVONIX side. Gamry seems like they are as well. We just think it's so useful for really rapid and effective probes into things like cell lifetime, overall performance, the kinetics, what's really going on inside the cell too, more so than just at the cell level, what's happening at the electrode level, what's happening at the different interfaces. It's just the amount of information generated is just mind-boggling. And I think really as a user, I can't stress enough how much the improvements in automation and flexibility mean that you can do brand new tests, you can do things that separate systems can't, and it kind of is really just at the limit of your creativity for what protocols you can design.
Great. So thank you, Jerome, Scott, and Connor. Before we launch into the Q&A, just a reminder to everyone, if you have any questions, to submit them using the Q&A button at the bottom of your screen. We've received quite a few coming in through the presentation, so I'm just going to jump into those. This one is for Jerome. Can Gamry eChem Analysis 2 fit EIS data automatically if we do not give circuit elements?
Right. So thank you for the question. So in eChem Analyst 2, and for everybody in the audience, that's the software that's used to analyze your data coming off of our instruments. So effectively, you need to know the circuit elements because you have to build that model before you can fit the data. But you can actually use what's called DRT, and that runs automatically, and it extracts out basically the number of time constants that you have in your impedance data. DRT is a distributed distribution of relaxation times, and so that can inform you on how you can build an equivalent circuit. But you have to have some kind of knowledge about the circuit so that the software doesn't do it automatically.
Thanks, Jerome. I'm not sure if this question is with regards to earlier plots shown or the later ones. So what software was used to create the EIS plots shown? Connor, you want to
Maybe I can answer that, Lori. I think we made the plots for this slide deck kind of offline using some of the general purpose graphing software that we like to use, but I don't think there's no limitation in terms of what an end user could. It's basically up to you. I think Gamry is very open with their software, or sorry, their data format. NOVONIX is very open, right? It's just column data, usually CSV, that sort of thing. So I know I very much enjoy using Gamry's visualization software. I think most users would be fine with that, but even something as simple as Excel is valid as well.
Right, and I'll add to that just because the data files that come off the Gamrys are tab delimited text files, so it's very easy to extract that data and use it as you like and however you want to, whichever software you use.
Okay, great. What are the testing best practices that must be followed with the UHPC and EIS system to ensure proper EIS results, like with not too much noise? Connor?
Yeah, I can talk a little bit about it from the integrated side, but in terms of just the purely making the best EIS measurement possible, I might, once I have my say, I'll maybe flip it over to Jerome as well, because I think he probably has better familiarity with that. So from our perspective, I think maximizing the value is, again, comes with controlling temperature. In one of the slides that we showed previously, you could see that if you're at a above room temperature, your EIS might not even have any much features. So if there's even a little bit of noise, you're not really gonna be able to resolve much. Other things like ensuring that you have the proper connections and making sure that you're not kind of flipping channel to channel and kind of being consistent with how the cell is connected. It's really a non-issue because we do provide our systems with cell holders that are 4-wire connected. So we're already setting people up for success. They do have the best connection if they just use our cell holders properly. But yeah, I suspect Jerome, I see him nodding, so I think he probably has something pretty useful to add.
Well, you're setting me up there, Connor. But no. It's actually the reason why the integration is so good. And that question speaks to it because the issues surrounding proper EIS results often is related to what Connor mentioned, is the connections, the cabling, the routing, and the fact that that stays the same throughout the testing and from cell to cell to cell. Because things like the ESR will change based off of how you connect to a cell. And so by having an integration, you basically remove that error, right? And that's important, I think. From the standpoint of the potentiostat, all of our potentiostats up to the end of the cell cable are fully shielded, and they are the accuracy is verified and vetted by us, and we work very closely with NOVONIX to ensure that that's maintained in the integration. And that's what you get there, right? So that's very important.
Thank you both. Does the NOVONIX Gamry interface allow the direct estimation of CEI, so slippage plus fade, from the experimental data, or data treatment must be conducted elsewhere?
Yeah, so I can probably take that one. So our raw data files, we just capture things like voltage, current, time. But we mentioned things like our UHPC protocol software and our UHPC control software, but we do have a third piece of software that completes our software suite. So that's UHPC plot, and that will extract things like cycle-based metrics from our data. And among those cycle-based metrics are things like the Coulombic inefficiency or the Coulombic efficiency, whichever one you prefer, and it will further break that down into things like fade and slippage. So it's something that is available through our software suite, but again, we're very open to their data format. So if you were looking to calculate it yourself, you're also more than capable of doing that.
Thank you. The integration of the UHPC and EIS system with climatic chambers was cited. Is there any temperature range where this system was tested? And does extreme temperatures negatively affect the quality of the results?
So I'd say this testing was limited to the spec of our thermal chambers. I would have to double check with Scott exactly what that is, but I think 10 or 15 degrees Celsius is the lower limit and 60 is the upper limit that we quote. But if you had another temperature chamber that could exceed those limits, there is no reason why this measurement couldn't be conducted in a different chamber. You will run into problems at lower temperatures, for instance, that when the electrolyte freezes, for instance, suddenly your cell will no longer function as a cell, and the EIS measurement, I suspect, would look pretty. It would change all of a sudden. Same thing with if you go to exceedingly high temperatures, the EIS won't be valid, and you might have things like catastrophic failure of the cell if you go too warm. But there's no reason why you couldn't connect this up with a different chamber.
And just to close off on that, our standard chamber is between 10 and 60 degrees Celsius for temperature range, but we also offer a wide range chamber that allows our customers to go down to minus 20 degrees Celsius and up to plus 60.
Thank you. How can one extrapolate the fastest data to obtain the long-term performance?
Yeah, I think I would recommend kind of adhering to some of the practices that we laid out. I think if you're trying to be as fast as possible, you would want to do things at very high temperature if you're trying to look at degradation, or at very low temperature if you're trying to find different kinetic stressors. I do think you have to be careful in terms of knowing what you're doing, that kind of thing. I think people discuss, for instance, Jeff Dawn's group does a lot of fantastic work at very high temperatures, projecting performance back down to room temperature, but they get their results very, very fast. I know there's an ongoing discussion about, do the results generated at high temperature translate back perfectly to room temperature? Are they truly predictive, and are you introducing any new failure mechanisms at those higher temperatures? So I think understanding the weak points of the system, if it's not temperature stable, you don't want to go to super, or maybe you do want to go to super high temperatures. Temperature is definitely a lever. If you know you have kinetic problems, maybe things like testing at higher rates are good. It more comes down to having an understanding of the cell and then designing the protocol around that.
Okay, thank you. Can you do EIS for EVs battery packs, not a cell?
I think there's a combined answer here. So I can say that NOVONIX's system, and therefore things that would plug into our integration, are limited to 5 volts. So our products are designed to look at the cell level typically. I do know, however, that Gamry offers an extended voltage range. So maybe Jerome wants to kind of just connect that into what his hardware is capable of in the absence of maybe the integration with NOVONIX.
Right. So that's correct, because the 5000 and that the EIS box 5000, they're limited to about 5-6 volts. So it's purely cell level testing. But for anything pack level or higher, we have what's just called the LPI 1010 system. Stands for load power interface, and they have a 100 volt. We have a 100 volt and a 1000 volt version, and that allows you to run impedance up at those voltages. And yeah, so it's certainly possible. It's an out-of-the-box solution for us. Yeah.
Does NOVONIX sell a complete unit without a potentiostat or multiplexer?
Yeah, I can take that. Absolutely, we sell these systems all the time, just on their own. Similar to obviously Gamry selling their systems on their own. We just wanted to make sure we highlighted today that that this integration exists. So for people that already have a UHPC that want to do this integration, they just need to get their hands on a Gamry unit and get a new cable from us. For our customers that already have a Gamry system that's compatible and want to add a UHPC, then you would just need to buy the UHPC directly from NOVONIX. So lots of no matter what equipment you have, I guess there's an option.
And although we have a list of more questions, we are going to wrap things up where we're at time. So thank you everyone so much for joining us today and for your great questions during the Q&A. We hope you found the session informative and insightful. This recording, as I mentioned earlier, will be made available on the NOVONIX website. This is the third installment of our 2025 webinar series. If you were unable to attend the previous sessions on either cathode materials or our research and development services, you can find recordings available on demand on our website or social channels. On behalf of the entire NOVONIX team, thanks again for being here. If you have any follow-up questions or would like more information, please don't hesitate to reach out. Have a wonderful day.